Hi, this is Tommy, and I'm going to be going over my responses for the graphs assessment. So for question one, we're asked to evaluate the overall runtime for this algorithm that traverses a adjacency-less representation of a graph. So here, we how this algorithm works is that we loop through every point, and for each point, we loop through all the vertices that it's connected to. So here, you may think that the runtime will be v times e, since we're doing a for loop, once looping over v and the other looping over e. But that is not the case, because for each point, we're only looping through a portion of e. So but in the end, we're still going over, we're still looping over all the e's and all the points. So in the end, the overall runtime would be theta of v plus e. And the next question is kind of about the same situation, except it asks us the worst case runtime, the big O bound for the worst case runtime, but only in terms of v. So in this case, we would be having a totally connected graph. So each each vertex is connected to every other vertex. In this case, we're maximizing the number of edges, and here the number of edges would actually be it would be choosing two vertices from all vertices, because all an edge is just a group of two vertices. So here the number of edges can be expressed as v times v minus 1 over 2. And this gives us a quadratic number of v's that we have to look through. So in the worst case, we'll be bounded by big O of v squared. Okay, so the next question asks us to traverse this graph with breadth first search. So initially we have 0 added to the perimeter and 0 in the visited set. So the first step is to remove 0 and add 1 and 4, because those are 0's neighbors. And visited set would of course be added with 1 and 4. And we do the same, and we keep repeating this process. We remove 1, add 1's neighbors, which are 2 and 3. So 1 will be removed, and 2 and 3 will be added. And here, and I kind of drew the arrow before, but here, the next step would be removing 4 and adding 4's neighbors. So 4 will be removed, and 4's only neighbor that's not in the visited set would be 5. Now we just keep repeating. Remove 2, and add 6. So 2, 3, 5. I mean 3, 5, 6. And at this point, 3 does not have any neighbor that we haven't looked yet, so 3 would just be removed without adding anything. And that will actually be the case with 5 and 6 as well. So that's how we ended up with this breadth first search order. So the next question asks us a modified version of breadth first search, which instead of adding the node immediately when we add it to the perimeter, as we've just seen, we're adding it when we remove it from the perimeter. So this actually wouldn't work, because it's very possible that you can end up with repeated nodes in your perimeter and end up printing them more than once. So how that happens is, if you do the same thing, if you do it on the same graph and start with 0, you would be well, first you remove 0, so this gets 0. You remove 1, so it has 1. You remove 4 and adds the neighbors of 4, so 2 and 3 would be added. So only this is at this point would only have 0, 1, 4 in it. Now once we remove 4, we would add the neighbors of 4, which would be 2 and 5. So here it wouldn't be just 5, it would have 2, 5. And as you can see, that's how we ended up with a duplicate 2. So the next question asks us to perform depth first search on the same graph. So we would be starting out at 0, and we're going to explore 0's neighbors. So first we're going to recurse on 1. So at this point, the digit set would look like 0. And once we recurse on 1, we would add 1 to the digit set, and 1's neighbors would be 2 and 3 that are because we're excluding 0. So now we are going to explore 3 after we explore 2. So 2, adding it to the digit set, we find that its neighbors are 4 and 6. So 4 and 6 will be added. And with the same procedure, we explore 4. So 4 only has 5. And when we explore 5, 5 has no neighbors. So we're done with 4. And now we go back to the other one where the most recent node that we haven't explored, so that would be 6. And 4 and 5 would already be here. And 6 doesn't have any neighbors that we haven't looked at yet. So 6 would just instantly finish recursing. And so 2 would be done. And now we go to 3, and 3 also doesn't have any neighbors we haven't looked at yet. So it would also finish immediately. And now we're done with recursing on 1, and we go to 4. But as you can see here, well, 6 is added in the previous step, and now we see that and 3 is also here. So now we see that all the neighbors of 4 has already been visited. So the order 4 will just be executed immediately, and that's how you end up with this order. And the next question, so here it is asking us to, instead of adding the node to the visit set before recursing on it, what happens if we do it after recursing on it? So a simple counterexample would be a graph like, well, 0 to 1, and in which case you would be exploring 0's neighbors and not adding it to the visit set, so you would end up exploring 1. But when you explore 1, you're also not adding it to the visit set, so when you explore 1, you are going to explore 0. But in this case, so you would obviously have a infinite recursion. And that's everything. Thank you for listening.